Imagine you're building an AI agent and you ask it to download a dataset, transform it, and create visual reports. That's not one task, it's three, each requiring a different tool. Now imagine your agent has access to thousands of tools, contributed by a sprawling community ecosystem. Which ones does it pick, in what order, and how does it even know how to break the problem apart in the first place? This paper tackles exactly that puzzle, and the answer turns out to hinge on something surprisingly subtle. Getting the decomposition right is far harder than getting the retrieval right. The setup is what the author calls compositional skill routing. The agent has a library of skills, reusable tool specifications following Anthropic's skill.md format, which are basically structured natural language documents describing what a tool does, when to use it, and how. Given a complex user query and a library of, in this case, 2,209 real skills harvested from the public model context protocol ecosystem, the agent needs to decompose the query into atomic subtasks, retrieve the right skill for each one, and compose them into an executable plan. Prior work has mostly studied single skill selection. Pick the one best tool, using bi-encoder retrievers or hierarchical routers. There's also work like Craft that builds query-specific toolsets via large language model filtering, but it treats this as a flat mapping rather than an ordered chain of dependent steps. None of these jointly handle the decomposition, retrieval, and compatibility problem. The proposed framework, called SkillWeaver, has three cascaded stages. First, an instruction-tuned LLM, Quen 2.5 7b instruct in the main experiments, decomposes the query into an ordered list of atomic subtasks, each meant to require exactly one skill. Second, a bi-encoder retriever, specifically the all-mini-LM-LX v2 model producing 384-dimensional embeddings, encodes each subtask and uses FAISS for fast cosine similarity search against the skill library. The retriever can encode skills using just metadata, name and description, or with the full body text. Third, a compose stage picks the final skill per step by combining retrieval relevance with inner skill compatibility, where compatibility is measured through things like input-output type matching, category overlap, and keyword co-occurrence. Dependencies between steps are detected, and a directed acyclic graph is built so independent steps can run in parallel. Now, here's where the paper's most interesting finding emerges. When the author runs the vanilla pipeline, retrieval looks mediocre. Only 34.2 out of steps surface the correct category skill in the top one position. But digging into why reveals something striking. The LLM is producing the wrong number of subtasks half the time. Strict decomposition accuracy is just 51%. And when you condition only on queries where the step count is correct, retrieval quality jumps significantly. The decomposer is the bottleneck, not the retriever. The large language model produces generic, fuzzy subtask descriptions that don't align well with how skills are actually named and described in the library. The fix is called Skill-Aware Decomposition, or SAD, and it's essentially a feedback loop between retrieval and decomposition. Think of it like writing a research proposal blind versus writing one after you've skimmed the available literature. Once you see what vocabulary the field uses, you naturally phrase your plan in terms it can match. SAD runs the vanilla decomposition once, retrieves the top 15 candidate skills for each subtask, and then reprompts the LLM to redo the decomposition with those skill names and descriptions visible as hints. Critically, this is input-side feedback. It corrects the plan before retrieval is finalized, which differs from methods like self-reg or React that feed retrieved evidence into the output side to refine generation. The author argues this direction is harder but uniquely suited here, because the real problem is matching the decomposer's vocabulary to the skill pool's vocabulary. The procedure is a fixed-point iteration over a finite hint space, so it provably converges, and in practice, one iteration captures most of the gain. The results are substantial. SAD lifts decomposition accuracy from 51% to 67.7%, a 32.7% relative improvement with a Wilcoxon p-value below 10 to the -6. Top one category recall moves from 34.2% to 37%, and when you condition on correct decomposition, it rises to 41.2%. A particularly clean ablation pins this down. When the author gives the vanilla model an Oracle prompt telling it exactly how many steps to produce, Decomposition accuracy hits 99.3%, and top 1 category recall reaches 39.8%, almost matching SAD's conditional performance. This means SAD is fundamentally a granularity corrector, not a vocabulary aligner. It works by getting the model to produce the right number of steps, not by teaching it better word choices per step. The context window savings are dramatic too. Exposing all 2,209 skills would cost about 884,000 tokens, while SkillWeaver reduces this to a few thousand, over a 99% reduction. There are a few more findings worth flagging. SAD transfers well to unseen skills. When the author holds out 2 entire categories or randomly removes 20% of the skill pool, SAD still delivers 35.6% and 23.2 relative gains respectively, showing it learns vocabulary level patterns rather than memorizing specific skills. Counterintuitively, the larger QN 2.5 to 14b model performs worse than 7b on vanilla decomposition because it over-decomposes, producing 4.72 steps on average versus a ground truth of 2.94. And SAD's hints anchor it back to the right granularity, yielding the largest absolute gain. A pilot using an LLM list-wise re-ranker on top of SAD's top 10 candidates lifts top 1 category recall by another 10.3% relative, suggesting cross-encoder re-ranking is a real lever for closing the remaining gap. On limitations, the compose stage is proposed architecturally but not evaluated in isolation because the benchmark lacks ground truth compatibility annotations. Only a pilot execution study shows 76.7% chain completion. Even with perfect decomposition, top 1 category recall plateaus around 4%, while top 10 reaches 79%, exposing a representation-level bottleneck the bi-encoder alone can't solve. The benchmark queries are template-generated, and while paraphrase robustness checks are encouraging, performance does degrade modestly on human-style queries. And the strict decomposition accuracy metric is harsh. Getting 4 steps when ground truth is 3 counts as a complete failure, even if the extra step is sensible. Now let's walk through some questions you might have after hearing all of this. First, why does feeding retrieval results back into decomposition help so much when on paper the LLM should already know how to break down tasks? The answer is that decomposition isn't really about logical reasoning here. It's about producing subtask descriptions whose vocabulary matches what's actually in the skill library. A vanilla model writes things like, process the data when the library has a skill called ETL pipeline transformer. Showing the model the actual skill names and descriptions from a first-pass retrieval gives it a glimpse of the target vocabulary, which mostly helps it pick the right granularity, the right number of steps at the right level of abstraction, rather than just rewording. Second, why is decomposition accuracy such a strict metric? And does it really matter if you're off by 1 step? Strict decomposition accuracy requires exact step count match, so producing 4 steps when the truth is 3 is 0 credit. The relaxed version that allows plus or minus 1 is more forgiving. It matters because step count gates retrieval. If you decompose a 3-step query into 5 subtasks, you're forcing the retriever to find skills for steps that shouldn't exist, which cascades into bad chains. The paper's DA-conditioned analysis shows retrieval quality jumps sharply when the step count is right, which is why granularity correction is so impactful. Third, if the retriever surfaces the right category in the top 10 70% of the time, but only at top 1 37% of the time, why not just always pass the top 10 to a downstream stage? You could, and the list-wise re-ranker pilot essentially does this. But there's a context cost and a latency cost to passing more candidates downstream. And at execution time, you eventually have to commit to 1 skill per step. The bi-encoder is fast and cheap for surfacing candidates, but it lacks the cross-attention needed to make fine-grained distinctions between functionally similar skills. That's why cross-encoder re-ranking on the top K is the natural next move. It's a small extra compute spend that recovers a lot of precision. For large-scale recommendation systems, the input-side feedback idea is the most directly transferable contribution. Think of a candidate retrieval pipeline where a user query, or a session intent inferred by an LLM, is decomposed into facets like category, brand, price range, and use case. Then each facet is matched against a catalog. Today's pipelines typically commit to a query understanding step and then retrieve. If retrieval surfaces nothing good, you're stuck. A SAD-style loop would do a fast retrieval pass, feed the top candidate item's actual attributes back to the query understanding model, and let it correct the granularity or vocabulary of its facet decomposition before final retrieval. This is especially powerful in long-tail catalogs where the gap between user phrasing and item metadata is huge. The context window result also matters practically. Production agentic recommendation systems are starting to expose tools to LLMs for things like personalized search, comparison, and action taking on behalf of users. Naively listing thousands of available tools or item facets blows the context budget. A bi-encoder retrieval layer over skill or tool metadata, surfacing just a handful of relevant candidates per subtask, with FAISS for sub-15 millisecond latency, is exactly the pattern you'd want for real-time serving at billion-user scale. And the finding that lightweight metadata embeddings carry most of the discriminative signal means you don't need expensive full document encodings. A major win for index size and refresh latency when your catalog or tool library changes constantly.